Hello everyone, my name is Nazrul Hasbi and my teammates Nur Atira Shohada and Nur Amalia, and we are from Group 14. Will be presenting about prostaglandin. In this presentation, we will be discussing about the introduction of prostaglandin, three mechanisms of reaction, which are the catalytic hydrogenation, next is the oxidation with Des-Martin peroxide, and lastly, the acidic hydrolysis, or also known as the deprotection. Next is the feasibility consideration, and lastly is the conclusion. Into the introduction. So prostaglandins are lipids that exhibit hormone-like properties, and it is a class of organic compound consisting of fatty acids or their derivative. Naturally, our body produces prostaglandins from a fatty acid called arachidonic acid, and they coordinate various bodily functions telling our body what to do and when. Prostaglandin play a role in the natural physiology of the body as well as in defense and repair. While synthetically, healthcare providers use several different kinds of synthetic prostaglandins as medication for a variety of conditions and situations, including travoprost that can treat glaucoma and elevated eye pressure, dinoproston that can help dilate the cervix in pregnant women who are at or near term, which help to induce labor, alprostadis, which belong to a group of medicine called vasodilators, and help to increase blood flow by expanding blood vessels. Next is the misoprostol that helps to treat postpartum hemorrhage, and lastly the iloprost which help to treat pulmonary hypertension and limited scleroderma. The reasons we are choosing prostaglandin for our presentation is because firstly, it has a clinical relevance and therapeutic value, which make them FDA approved and widely prescribed and medically essential. Next is because of their structural complexity, which include multiple stereo centers, functional groups, and sensitive motif, making them challenging target for synthetic chemistry. Next is their opportunity for synthetic innovation, which help to demonstrate the utility of the rearrangement as a central step in forming prostaglandin-like framework, and lastly for the drug analog development because they are well-characterized drug and serve as ideal platform for creating analog with improved pharmacokinetics or fewer side effects.
Hello everyone, my name is Noadra Shuhada bintu Rahmat and I will be presenting the mechanism for reaction 1 in the synthesis of prostaglandin E1, which is the catalytic hydrogenation step using palladium on carbon and hydrogen gas. This reaction is important because it helps reduce a double bond to a single bond while maintaining the correct stereochemistry, which is the critical for the biological function of prostaglandin. So let's begin with step 1. For step 1, which is activation of hydrogen, the hydrogen gas molecule approach the palladium on carbon catalyst surface. A curved arrow shows the electron in the HH bond moving toward the palladium surface. This causes the bond to break and each hydrogen atom become absorbed on the surface. This is called dissociative adsorption. Now the palladium surface holds two reactive hydrogen atoms, which is ready for addition step. Next, for step 2, which is alkene adsorption, the alkene, which is a molecule with a double bond, approach the same PD surface. The pi electron in the double bond interact with the palladium catalyst. In the slide, I show a curved arrow from the double bond to the PD surface. This weakens the pi bond and align the alkene flat on the surface for reaction to occur. Next is step 3, which is syn addition of hydrogen. In this step, both hydrogen atoms that were absorbed on the catalyst surface now add to the double bond. A curved arrow shows one H go to each carbon of the double bond, but both from the same phase. This is called syn addition. The result is that the double bond become a single bond, forming an alkene. The stereochemistry is preserved, which is very important for the biological activity of prostaglandin. Last step is product desorption. Finally, the new alkane molecule, which is the hydrogenated product, detached from the catalyst surface. The bond between the product and the PD catalyst breaks and the product leaves the surface. This step regenerates the PD catalyst, allowing it to be reused for the next reaction cycle. So, in summary, catalytic hydrogenation works by first activating hydrogen on PD catalyst, then coordinating the alkene, adding hydrogen from the same site, and finally releasing the saturated product, all while maintaining important stereochemistry.
Hello, I'm Amalia. So in this section, we'll focus on the reaction 2, which is the oxidation of alcohols using desmartine periodinane, which is DMP. So this reagent is a hypervalent iodine compound that allows for the mild and selective oxidation of alcohols into carbonyl compounds. So specifically from primary alcohols to aldehydes and secondary alcohols to ketone. So for our product is secondary alcohols to ketone. So this oxidation is often used in the synthesis of complex natural products. So our product is prostaglandin E1. So where the mild condition and functional group tolerance are especially valuable. Okay, so let's begin with the first step of the mechanism, which is the activation of the alcohol by the DMP reagent. So here the lone pair of the oxygen of the alcohol attacks the electron deficient iodine center in the DMP molecule, desmartine molecule. So this is a key nucleophilic substitution step where the alcohol depletes one of the acetate ligands on iodine. So this results in the formation of high energy intermediate called N-alkoxyiodine, in which the alcohol is now covalently attached to the iodine center. So this structure sets the stage for the elimination process that follow after this. So the presence of DCM, which is the dichloromethane as the solvent, is crucial here because DCM is a polar aprotic solvent. So it doesn't form hydrogen bonds with the alcohol, so it leaves the lone pairs on the alcohol oxygen free and reactive. So it also helps dissolve both DMP and the alcohol, ensuring efficient mixing and reaction. So in the second step, which is a base, typically acetate ion, ACO minus, which is already present in the reaction mixture, it will abstract the proton from the alcohol group. So this deprotonation has two important outcomes. The first one is it increases the nucleophilicity of the alcohol oxygen, enhancing its binding to iodine, and also it leads to the formation of the first equivalent of acetic acid, which is the SCOH. So this is an important mechanistic details because it explains where one of the two acetic acid molecules come from this reaction. Now we move on to the third and final step, which is a type of E2-like elimination reaction. So another acetate ion now act as a base and abstract the alpha hydrogen from the carbon adjacent to the alcohol oxygen. At the same time, a concerted electron shift occurs, so which is the electrons from the CH bond move to form a C double bond O bond, while the CO bond to iodine breaks. So this results in the formation of the desired carbonyl compound, which is ketone, since we start with the secondary alcohol. So in this process, a second molecule of acetic acid is also formed. So what is the role of DCM solvent? So throughout this process, DCM, which is dichloromethane, plays an essential role, which is the first one is it stabilizes the intermediate and transition states. Second is it does not interfere with the reaction by hydrogen bonding. The last one is it evaporates easily during work-up. So, however, DCM also poses safety and environmental concern, which leads us to our next discussion. after this, which is the operational cost and hazard of using this method.
Lastly, the third reaction, which is known as the acidic hydrolysis or deprotection, which use the reagent from the past reaction to react with hydrofluoric acid in the estronitrile and water to become prostaglandin E1. Step 1 is the protonation of the ether oxygen by using fluoric acid. So, hydrogen will act as a delta positive and donate proton to the oxygen atom of the silane ether, increasing the electrophilicity of the silicon, followed by the nucleophilic attack on silicon, which make the fluoride ion from the hydrogen fluoride to become nucleophile and attack the silicon center, which act as the electrophile, since silicon has a high affinity for fluoride, forming a strong silicon fluoride bond. The result is cleavage of the silicon oxide bond and formation of the free alcohol, which known as the prostaglandin E1.
Now, I will explain the feasibility consideration for each of three reactions involved in total synthesis of prostaglandin E1. For reaction 1, we use a palladium catalyst, which is known to be expensive. Since this is a pharmaceutical synthesis, the catalyst must be removed from the final product to meet safety standard. The reaction also involves hydrogen gas, which is highly flammable and must be handled carefully. It requires special equipment such as a hydrogenation setup or pressure vessel. However, if the laboratory is fully equipped and follows safety protocol, this reaction is considered safe and feasible. In reaction 2, we use Dess-Martin periodinane, which is very expensive reagent. It is also sensitive to air and moisture, so it must be handled in dry condition. This reaction produces toxic iodine-containing waste, which require proper chemical waste disposal. Because of this factor, this reaction is generally only feasible for small-scale reaction for the synthesis of high-value compound like prostaglandin. Reaction 3 involves hydrofluoric acid, which is extremely toxic and corrosive. Working with hydrofluoric acid requires strict safety measures, including PPE, a fume hood, and having calcium gluconate gel on standby in case of exposure. This reaction also has a long reaction time, around 6 hours, which increases supervision and cost. Additionally, it requires pH control during the workup to prevent product degradation. Overall, this step is only feasible in well-controlled laboratory environment with trained personnel and proper safety facilities. Next, for advantages and disadvantages for each reaction. For reaction 1, one of the main advantage is that it is stereoselective, specifically giving syn addition. This is important because it helps control the 3D shape of the molecule, which is crucial for prostaglandin's activity. The reaction is also clean and efficient, producing only the alkane as the product with minimal byproduct. However, there are a few disadvantages. Since it uses a metal catalyst, there is a risk of metal contamination, which must be removed from the final pharmaceutical product. The use of hydrogen gas also brings safety concerns, especially under pressure, requiring careful handling and equipment. For reaction 2, the main advantage is that it is highly selective, converting alcohol into ketones without affecting other sensitive functional group. It is also done at room temperature, which makes it gentle and suitable for complex molecules. On the other hand, this reaction has some disadvantage. It raises environmental and waste concern, particularly because it produces iodinated byproducts. The reagent is also sensitive to moisture and air, meaning the reaction needs to be performed under dry conditions. Reaction 3 has a few important advantages. It allows for the efficient removal of protecting group, which is necessary for moving forward in synthesis. It also enables ring cyclization, forming the final prostaglandin ring structure. However, there are some drawbacks. The hydrolysis condition can be harsh, which might affect sensitive part of the molecule. There is also a risk of overreaction or side reaction, especially if the pH is not well controlled.
Now let's look at the operational cost consideration in the synthesis of prostaglandin E1. So for reaction 1, catalytic hydrogenation requires expensive catalysts like PD or carbon or PTO2. It also needs pressurized hydrogenation equipment and strict safety controls due to flammable gas. So this makes it moderate in operational costs, mainly due to the infrastructure. So moving to reaction 2, which uses DMP, which is desmartin per iodine. The reagent is effective but costly. So it also requires dry condition and produce toxic iodinated waste that needs proper disposal. So while it is efficient, this step has a high operational cost. So lastly, for reaction 3, the hydrolysis step use affordable reagent like acetic acid or water. Although it may require careful pH control, the process is generally safe and generates unique byproducts. So overall, this step has a low cost operation. So these differences highlight the importance of balancing efficiency with practicality when planning a total synthesis. So finally, we briefly touch on the idea of alternative pathway. In complex synthesis like this, it's often useful to consider route adjustment based on cost, safety, scalability, and selectivity. So for example, we can use using a greener oxidants instead of DMP, which is desmartin per iodine. We can use hydrogen instead, or switching from hydrogenation to organocatalytic reductions could reduce the hazards and the cost. So this alternative may not always be feasible in every lab, but they show how flexible and evolving modern synthetic planning can be. So especially for pharmaceutical targets like prostaglandin. Finally, the conclusion of this reaction and mechanism is the total synthesis of prostaglandin E1 demonstrates the strategic integration of catalytic hydrogenation, desmartin oxidation, and acidic hydrolysis or deprotection steps to achieve a highly functionalized and stereochemically rich target molecule. So each reaction offers unique advantages such as the stereoselective syn addition from hydrogenation, the mild and selective oxidation by DMP, and the efficient unmasking of hydroxyl groups through hydrolysis. So, however, these transformations are not without challenges. So, catalytic hydrogenation requires a specialized equipment and pose safety concerns due to pressurized hydrogen. While desmartin oxidation, it is effective, but it involves high reagent costs, air sensitivity, and hazardous iodine waste. And acidic hydrolysis, although it low in cost, but demands careful pH control and safety measures due to the use of corrosive HF. So overall, the pathway is synthetically feasible but requires careful planning, especially in managing the operational costs, safety protocols, and purification strategies. So despite these constraints, the methodology showcases valuable tools in complex molecule construction and highlights the practical consideration necessary for laboratory scale prostaglandin synthesis. That's all from us. Thank you.